Hello and welcome to this lesson on secure coding practices. In this chapter, we'll cover various secure coding practices essential for developing secure applications.
We'll explore declarative versus imperative security, bootstrapping, cryptographic agility, handling configuration parameters, memory management, error handling, and more.
Let's dive in.
Secure coding practices are a key element in the development of a secure development lifecycle.
Building upon the foundations of requirements and the variety of implementation models,
we'll examine specific coding practices that can be employed to achieve higher levels of secure code.
First, let's discuss declarative versus imperative security.
Declarative security specifies what needs to be done, not how.
An example of this is SQL, where you describe the task and the engine handles the execution. This method allows for flexibility in deployment and is managed by operational personnel rather than developers. On the other hand, imperative security embeds security within the code itself.
This allows for granular security measures for complex business rules but can make the code less portable due to specific logic embedded within.
Next, we'll talk about bootstrapping.
Bootstrapping refers to the process that occurs when a computer or program starts up. This includes activities like power-on self-test routines, bootloaders, and OS initialization. Ensuring the security of this process is crucial as malicious software can interrupt it. Using configuration files to manage startup elements and keeping them under application control can help secure the startup and operational aspects of the application. Cryptographic agility is another crucial topic. Cryptographic agility is the ability to switch cryptographic algorithms without changing the underlying code. This allows for quick replacement of insecure algorithms and is typically implemented via configuration files.
Cryptographic agility ensures compliance with international cryptography standards and is critical for maintaining security as cryptographic standards evolve. Now, let's move on to handling configuration parameters. Configuration parameters can alter the behavior of an application. Securing them is vital as they can change programmatic behaviors. Critical parameters should be protected, possibly encrypted, and controlled by access control lists. Always validate and test the handling of configuration data to prevent unauthorized changes.
Memory management is another essential aspect of code security.
Managed code applications handle memory automatically, reducing risks.
However, unmanaged code requires developers to handle memory allocation, garbage collection, and preventing memory overflows. Complexity in memory management can lead to security vulnerabilities, such as buffer overflows.
Error handling, also known as exception management, is crucial. Applications must detect and handle errors to prevent failures. Proper error handling ensures that unexpected conditions are managed gracefully.
Exception handlers should log errors without exposing sensitive information.
Interface coding is critical for secure application interaction. APIs, or application programming interfaces, must be designed securely to prevent attacks. Input validation and proper authentication measures are essential. Review and secure third-party APIs to prevent vulnerabilities. Primary mitigations for secure coding include locking down your environment, controlling all inputs and outputs, and assuming external components can be subverted. Use industry-accepted security features and integrate security into the entire software development lifecycle. Employ a mix of methods to prevent weaknesses. Learning from past mistakes helps in updating security requirements and preventing repeat errors. Keeping the development team's knowledge up to date with industry best practices is essential. Implementing secure design principles requires specific design elements. Use information from attack surface analysis and threat models to pinpoint where specific design elements can be employed to achieve desired security objectives. This includes controls to ensure confidentiality, integrity, and availability. When designing security aspects of an application, ensure security measures are proportionate to the actual risk. This is known as good enough security. Least privilege is a fundamental security approach.
It limits access rights to the minimum necessary and should be a design standard. Separation of duties must be designed into a system, requiring multiple conditions to be met before a task is complete.
Defense in depth uses multiple layers of security controls to mitigate a wider range of threats.
Fail-safe design ensures systems fail to a secure state, maintaining security attributes like confidentiality, integrity, and availability. Economy of mechanism emphasizes simplicity in design, making applications easier to secure.
Complete mediation ensures authorization checks are performed for all sensitive operations. Open design involves open communication and documentation, preventing later activities that could weaken security efforts. Least common mechanism prevents security failures by avoiding shared mechanisms between multiple processes. Psychological acceptability ensures security measures are user-friendly, preventing users from working around them. Every system has a weakest link. Identifying and strengthening these parts is crucial for overall security. Leverage existing components by reusing trusted components to enhance security and reduce development costs. Finally, design systems to avoid single points of failure, preventing catastrophic failures from occurring. Session management involves securing communication channels between program elements. Exception management handles programmatic responses to errors, ensuring proper error logging and handling. Configuration management involves securing the configuration of a system by securing files and other elements. Avoid cryptographic failures by using approved cryptographic libraries and ensuring proper implementation of cryptographic functions. Hard-coding passwords, keys, and other sensitive data into programs is a serious security risk and should be avoided. Ensure encryption of sensitive data is properly implemented to protect against unauthorized access. Use only approved cryptographic algorithms and key lengths to prevent the use of broken or risky cryptographic algorithms. Always perform integrity checks on downloaded code to ensure it is correct and from a trusted source. Use a one-way hash with a salt to protect data like passwords from unauthorized access. Input validation is the most important defensive mechanism, treating all inputs as hostile until properly validated. Output validation ensures that data leaving the application is correct and secure. Prevent buffer overflows by validating input sizes and writing solid code. Canonical form involves ensuring input data is in a standardized format, preventing issues with different character encodings. Finally, ensure all defense functions such as authentication and authorization are properly implemented. Secure coding practices are foundational for developing secure applications. By adhering to these principles and continuously learning from past mistakes, developers can create robust and secure software systems. Implementing these practices throughout the software development lifecycle ensures a proactive approach to security. Thank you for watching this lesson on secure coding practices. Remember, security is a continuous process, and staying informed about best practices is key to maintaining secure applications. See you in the next lesson.